All right. So day 3 of Math 3 Module 1 is about inverse functions. And we're going to start basic in this lesson. In the next lesson, we'll get a little more complicated. So inverse of a function. Suppose that f is a one-to-one function, so it has to be one-to-one. Then, to each x in the domain of f, there is exactly one y in the range. Okay, and to each y in the range of f, there is exactly one x in the domain. The correspondence from the range of f back to the domain is called the inverse of the function, and the symbol is f to the negative 1. I know that sounds like gibberish right now, but the key part here is to understand we have a one-to-one function, we have inverse, and the symbol for inverse is right here. All right, so maybe these examples will clarify the definition for you. So when we go to find the inverse of, say, a map, okay, like this one here, what's basically going to happen is we're reversing the order in which the x and y become. So now this becomes my new x value, this becomes my new y value. So if we had to write the inverse in a map again, I'm going to go 6.2, 6.1, 0.8, 8.3, 5.8, and now we're going to map these new inputs to the old inputs. So this would be Indiana, this would be Washington, this would be South Dakota, this would be North Carolina, and then Tennessee. Okay, and that would be the inverse of that function. Now, finding the inverse of a function defined by a set of ordered pairs. Once you look at your set of ordered pairs, again, all we're doing is flip-flopping the x and y here. Okay, so the new inverse would be flip these, and that becomes the ordered pair negative 27, negative 3. The next ordered pair would be negative 8, negative 2. Then negative 1, negative 1, 0, 0, 1, 1. This would become 8, 2. This would become 27, 3. If you look, all I did was flip-flop these x and y values. Now, my new domain for this inverse function would be negative 27, negative 8, negative 1, 0, 1, 8, and 27. My new range for the inverse function would be negative 3, negative 2, negative 1, 0, 1, 2, and 3. Okay? Now there are a couple of things I want you guys to remember about the inverse functions. In an inverse function, the domain of the function ends up being the range of the inverse. And the range of the function becomes the domain of the inverse. That's the idea behind flip-flopping the x and y's when we go to find the inverse. Now, another important thing is if you go back to the first section in this, and we talked about composite functions, if I do f inverse of f of x, or of f, sorry, anytime I evaluate that with an inverse function, it should equal x. And I must also look at if I do f of f inverse, that should equal x when you simplify the expression. So if you compose the function and its inverse and you simplify that expression, you should get x. The last thing is the graph of a one-to-one function f and the graph of its inverse are symmetric with respect to the line y equals x. So if I look at the line y equals x here, and then you look at the function, and then you look at its inverse, if you look, it's basically a reflection over the line y equals x. And anytime you reflect over the line y equals x, what happens to your y and value? X and y values, they flip-flop. Okay, so let's take a look at this. So how would we verify that g of x and g inverse of x are inverses? Well, the first thing I'm going to do is I'm going to evaluate g of g inverse x. So what is g inverse of x? That's this here. So what I'm going to do is plug that in the place of x and g of x. So when I do that, I would get the cube root of x all cubed. And what does that equal? Well, raising a cube root to the third power eliminates the cube root, and we're just left with x, right? But now I have to check, is g inverse of g of x also going to equal x? So if I go to do this one, now anywhere we see an x here, we're going to replace it with x to the third. So we're going to do the cube root of x to the third. What does that give me? X. When we compose the function and its inverse, and when we compose the inverse and the function, do we get x? Yes. Therefore, we verified that these are inverses of each other. Now, example 4. This is a little bit more challenging. Okay, so let's take a look at it. It says, verify that the inverses of f of x and f, this should be inverse, right, of x. For what values of x is f inverse f of x equal to x, and for what values of x is f of f inverse x equal to x. Okay, well, the first thing we have to show is that these are inverses. So the first thing I'm going to do is I'm going to do f inverse of x and verify that. Now the algebra here can get a little bit complicated. So I'm going to try and color code this the best I can. But I'm plugging f inverse of x into f of x. So let's take a look at this. So if I have 1 over, I'm replacing this x now with this function. So this is going to be 1 over, it's going to be 1 over x plus 1, but then I still have to subtract this 1. Now, if I simplify this, it should equal x. Well, if I look, this ends up being 1 minus 1. So I really have 1 over x here. And remember, this is no different than if I write 1 divided by 1 over x. Okay, so I'm taking 1 and dividing it by 1 over x. That now can be rewritten. Remember, dividing is the same as multiplying by the reciprocal. So if I change that to 1 times, what's the reciprocal of 1 over x? It's x over 1. What is 1 times x? X. So that one works out. But now I have to do f inverse of f of x to see if this works out. So now, if I look at it, that's going to be 1 over. Everywhere I see an x here, I'm going to kick it out and replace it with this 1 over x minus 1. But then I still have that plus 1 on the outside here. Okay? So now, if I go to simplify this, the 1 over x minus 1 plus 1, we are going to rewrite that as 1 divided by 1 over x minus 1 plus 1. But then we're going to take this division, change it to multiplication. So it'd be 1 times x minus 1 over 1 plus 1. Now this is just going to give you x minus 1 plus that 1, and right away these eliminate each other, and that equals x. But here's the thing, right? When we look at the domain of the first one, now when we look at the input value here, f of x, right here, remember, what did we input? 1 over x plus 1. If we look at where this function does not exist, this does not exist for x value, the x value 0, because what would 1 over 0 give me? It would give me it would be undefined. Therefore, we have to exclude the values x such that x cannot equal 0. That's for the first part. Now for the second part, we're going to say x such that x, if I look here, what can this not equal? Well, we cannot have that denominator equal 0. Therefore, x such that x cannot equal 1 here. All right, so when we talk about for what values of x is that, well, here's the thing, is that every value except when x is equal to 0 or x is equal to 1. So we cannot have those part of our domain. Okay? And example 5 here. The graph below is that of a one-to-one function, y equals f of x. Draw the graph of its inverse. Well, if I look at it, we set up above that this ends up being a reflection over the line y equals x. So if I draw that line in there, I'm going to reflect these ordered pairs over that. And remember, when I do that, all I am doing is flip-flopping these ordered pairs. So instead of 1, 2, 1, now I'm going to go 1, 2. And that's one of my points. Then my next one, if this one's negative 1, 0, that means I'm going to go 0, negative 1. And then the last one, negative 2, negative 1, will become negative 1, negative 1, negative 2. And right away, messed that up. Meant to go from here to there, and then to here. And if you look, that is a reflection over the line y equals x. Okay, go ahead and attempt the homework, and if you have any questions, let me know.